Okay, so good morning, everybody. Seems like it has been a very long time, and I suppose Thursday to Tuesday, Friday to Tuesday, right? Friday, Saturday, Sunday, Monday, Tuesday, 4 days. That is a long time. In the last lecture, I talked about transformation, electric and magnetic fields, right? And I think that class was probably not something that most of you probably did not enjoy because it was all very dry. It was just all mathematics. And the problem with physicists such as you and me is that we don't like too much mathematics. If we like mathematics so much, then we would not be doing physics, right? We would not be doing physics. So physicists would be mathematicians, who just couldn't handle the rigor. So so there is a very nice and very simple physical way to understand the same results that I obtained in Friday's lecture. And that's what I'm going to talk to you about today. And it is by means of something that you're all very familiar with, which is what is known as a Gedanken experiment. At least I hope you're all very familiar with it. Right? And this is a German word. Obviously, the first part is the German part. Second part is common. This is called a thought experiment. Gedanken, in thought, I suppose, in German. So, and of course, people have been conducting thought experiments in our own head from the moment that as living beings we gained self-awareness, right, or awareness. So everybody conducts thought experiments. All living beings essentially. Even a cockroach conducts a thought experiment. It's like thinking, though, will I find food there? What will happen when I go in that direction instead of this direction? If I go in that direction, will I find food, or will I find somebody's slipper coming down on me? That's a thought experiment, right? These were popularized, of course, by Einstein, right? They became famous after Einstein's work because he didn't have any experimental input. He relied entirely on his imagination. So we are going to use a couple of thought experiments today to obtain the same results that we obtained in the previous lecture, and in a simpler fashion, hopefully. So in the last lecture, what we found was that if you look at the electromagnetic field from the perspective of a moving frame. So again, as usual, let me first set up the reference frame. Is it set up here? Yeah. Right. So again, you have two frames of reference, O prime and O. O prime is moving with some velocity v with respect to O. For the purpose of this thought experiment, we won't need, we will not need the test charge. So I'll remove that. I'll let that be. Now, so what we find is that E perpendicular, by looking at what do we do? How do we go about it? What is the hard way to solve the problem? Well, the hard way to solve the problem is the following, right? You say that you have a test charge, right? And the test charge feels a force due to the electric field, which is given by E prime times Q in the moving frame and EQ in the as seen by the observer at rest, right? And then from this we can write down the force 4 vector. So the force 4 vector F mu is equal to what is it, 1 by C d by dt. Again, let me remind myself what that expression for force 4 vector is. Right. It is gamma v dE, where this gamma v refers to the velocity of the particle. Okay, not the so so I should use gamma u actually, gamma u, and then this quantity is your normal non-relativistic force. Similarly, you will have the force 4 vector as seen by the moving frame, and it will have the same expression, right? The same form of the expression. And we know that these two will be related by a Lorentz transformation, right? This is the procedure. So when we do this, we equate the different terms, right? So we get a condition relating again. So when we do this, what we find is that the parallel component of F transforms in this way. The perpendicular component of F transforms in this way, right? And now we impose certain conditions on the charge. Depending on the condition we impose on the charge, we can look at the different components of the magnetic and electric field. So for instance, we say that in the first step, what do we say? We say that we set the velocity of the moving frame equal to the velocity of the charge in the original frame. We set these two, V and U, to be equal. If we set these to be equal, then U prime, the velocity of the charge in the moving frame, becomes 0, right? And also we say that the magnetic field in the original rest frame is 0. So here we have B is equal to 0. The reason we do this is so that there is no force on this charge due to this magnetic field in this frame of reference. Otherwise, we would have to transform that component. So here in this frame of reference, there can be a, well, so yeah, in the new frame of reference, there can be a non-zero magnetic field. But because the charge is at rest in this frame of reference, this magnetic field has no effect on the charge. Right? So this trick allows us to look at only the electric field component. And when we do that, we find that the electric field in the parallel direction is the same. Right? Then we do another trick. We say that what if we set the charge so yeah, okay, right. Then we look at the perpendicular component. The perpendicular component turns out to transform in this way. So this gives us the electric field transformation, which is that the electric field in the parallel direction remains the same, and in the perpendicular direction, it gets dilated by a factor of gamma, right? Then we want to look at the magnetic field, right? How does the magnetic field transform? Now here things become a little complicated, right? Because you have to use this equation and you're like, what is this equation? Where does this equation come from? I'm confused. Why is life so hard? Etc. etc. So today I'm going to talk about some thought experiments which will allow us to circumvent much of this mathematical machinery. And these thought experiments are as follows. You can also find them, by the way, if you are interested in the textbook reference. You can find them in chapter 12 of the textbook on electrodynamics by David Griffiths. Okay. Right. So what is the thought experiment? Well, we imagine again that in our we have two observers, etc., right? That all that remains the same. Now we imagine that there is a parallel plate capacitor. There's a parallel plate capacitor, and this parallel plate capacitor is at rest in the O frame, the original frame of motion. And the plates are oriented such that the x-axis, right, is parallel to the plates, and the perpendicular direction to the plates is, let's say, given by the z-axis, right? Now these plates have an area A, and let's say the distance between the plates is given by d, right? And the whole thing is connected to some circuit, right? So which will charge the plates, etc. Okay. Now the circuit really doesn't play a role in this, so I don't want to worry about the Lorentz transformation of the circuit, the current and all that. The circuit is just used to charge up the plates. Once the plates are charged, we disconnect the circuit. So we throw away the battery and the wires. We don't need them anymore. Right? The plates are not going to discharge until they are connected to some ground or some other until there is a path for the charge to go. So from our Gauss's law, we know that the electric field between these two plates. So let's say the upper plate has charge plus Q, minus plate, bottom plate has minus Q. According to the pattern of connection, that is what will be plus minus. So the electric field will point in this direction, right? In the negative Z direction. And assuming taking the approximation of infinite sheets of charge, which are very such that the size of the sheets relative to the distance between them is very large, we can say that this electric field, what happens, it becomes equal to sigma by 2 epsilon naught due to each plate, right? in the center of the center region, you get a contribution of sigma by 2 epsilon naught in the negative z direction. So the total electric field becomes minus sigma by epsilon naught. This is the total electric field, right? And this is equal to sigma is equal to the sigma is the charge density, the surface charge density. So this is equal to the total charge divided by the area by epsilon. Okay, this is a setup. Now we consider our moving observer O prime, and O prime is moving in the positive x direction with some velocity v. Okay. Now what happens to this electric field as seen by O prime, right? So we can look at these quantities again. So first of all, you might think that, well, because of the relative motion, the electric field vector might pick up some diagonal component, right? You might worry about that. You might say that the electric field picks up some diagonal component. So this is the upper plate, this is the bottom plate, this plus q minus q. And you might say that, well, what if the electric field picks up a diagonal component like this? Right? All right. So what would be the direction of the tilt, right? If you do have a tilt, what would happen? You would get the positive electric field tilting in this direction, and the negative electric field tilting in this direction. And now, why is this not working? All right. So the reason that these two fields tilt in this way, right? You might think that, well, why doesn't the electric field due to the negative charge tilt in the same way? So if this tilted in the same way, then what would happen? You would get the components in the parallel direction would add, and you would get a parallel contribution to the electric field also, right? So let's assume that the positively charged plates, right, and they are both moving with the same velocity, right? For the positively charged plate, the electric field tilts in this direction, right? So then you want to ask, how should the field look like for the negatively charged plate, which is also moving? Now, since you change the sign of the charge, what will be the electric field direction for this guy? The electric field direction for this guy will be the negative of this electric field, right? Because it's a negative charge, right? So the negative of this will imply that your electric field looks like this. And in this case, what will happen is there will be no so if you take the negative of this vector, you get this vector. If you take the negative of this electric field vector, you get this electric field vector, right? You can just think about this for 1 second and convince yourself that this is the case. This is the positive plate, and this is the negative plate. And so I'm saying that the electric field tilts like this, right? For the positive plate. So when I look at the negative plate, what should happen? The direction of the vector should be switched, right? So if this is E1, let's say, and E2, this vector has to be E1 minus, and this vector has to be E2 minus, right? So I hope that that is clear. So then in this case, what will happen is that the parallel components of these electric fields will cancel out, right? And you'll still be left with a perpendicular component. So what will be the perpendicular component of the electric field in this case? E prime is equal to, will be this, something which is similar, right? Which will be Q prime by A prime by epsilon naught Z, right? And epsilon naught is a constant, right? We're not going to change that. Q prime is also, the charge is not going to change. But what is going to happen is that the area is going to Lorentz contract, right? In the direction of motion. So you will get that Q is equal to Q prime, but A prime is equal to A, because it's contracting, divided by the gamma factor. So you can now easily write down what the perpendicular. Okay. I'm guessing none of you wants to watch a Korean drama at this time. The perpendicular component of the electric field will look like this. Minus, you will get a gamma factor over here, Q by A, epsilon naught Z, which is equal to minus, so I can write this as gamma V. And since this is a perpendicular component, right? Right. So we obtain the same result, that the perpendicular component is Lorentz dilated, without going into the transformation law for the force and all that. All right. Now we can repeat the same exercise, but what we do instead, as you might guess, is that we want to look at the parallel component of the electric field. So it's pretty obvious to see what one needs to do. We need to look at the same parallel plate configuration, but now we need to rotate the plate so that the direction perpendicular to the plate is now parallel to the direction of motion, the relative direction of motion, right? So everything else is the same. You have this area of the plate, you have some charge, plus Q minus Q. You have some electric field here between these two plates, and the distance between the two plates is D, right? Okay. Now, So we look at the same thing from the perspective of moving observer, O prime. What does the moving observer see? The moving observer will see that the area of the plates remains unchanged because the area is perpendicular to the direction of motion in this case now, right? So this is O prime, and the relative direction of motion of O prime is perpendicular to the area. So now what happens? A prime is equal to A. Q prime is equal to Q. Charge is not going to change. Wait a second. And so again, if you follow, the Gauss's law argument, this tells you that E will be equal to E prime. The only thing that will happen is that D prime will be Lorentz contracted with respect to D. The plates will appear to be closer together, right? But if you remember the derivation, if you look at the electric field in this approximation doesn't depend on the distance between the two plates. So it won't affect the result. So by means of this very simple thought experiment, we have found that E perpendicular is Lorentz dilated and E parallel remains the same, right? And once you do this derivation in this manner, I believe that you are much more likely to remember the result also. Okay. Any questions? Okay. So now we still have to look at the magnetic field, right? So what we will do is we will, one second. So in order to look at the magnetic fields, what we'll do is we'll look at the same configuration that we used for this case. Okay, we'll use this configuration. Now, what we will say is that these plates, so in the initial case, what we said was that these plates are at rest in our frame of reference, in the original frame of reference. Now we will say that these plates are they're both moving with some velocity v naught, right? With respect to this observer, with respect to the O observer, right? Okay. So now what will happen is, as seen by O, there is going to be an electric field, right? but there's also going to be a magnetic field, right? Why is there going to be a magnetic field? Because these moving plates, right, they give you a current density, right? So if you have a positively charged plate that is moving parallel to itself, that gives you a surface current density, right? And that surface current density I can write as K, right? And K is going to be equal to plus or minus sigma times V naught times X hat, right? So this is the surface current density. Okay. Now you can determine the electric field due to these surface currents. If you look at the plate edge on, what do you see? You see the plate is moving with some velocity v, right? So, and since there's a positively charged plate, that gives you a current in this direction, right? So what happens to the magnetic field? You can use the right hand rule, put your thumb in the direction of the current and curl your fingers around. So what you will find is that the magnetic field comes out of the page above the plate and goes into the page below the plate, right? So the magnetic field above the plate, this B, will point in we need some axes now. So let me say that this is the Z axis and this is the Y axis. So this magnetic field will point in the positive Y. This is coming out of the page, so that will correspond to the negative Y direction. Sorry, negative Y direction. Right? And what will be the value of the magnetic field? You can calculate that. I'll leave that as a calculation for you, which will be equal to mu naught sigma V naught, and the direction is Y hat. Similarly, the magnetic field in the positive direction in below the plate will be mu naught sigma V naught Y hat. What about the contribution from the lower plate? The lower plate is also moving at the velocity V naught. But now this corresponds to a current which is moving in the opposite direction, right? So what happens to the magnetic field due to this plate? It moves in the opposite sense, right? And so now you get B is equal to, you get a contribution to B in the middle from both the plates. So this adds, right? So if you look at the magnetic field in the center between the plates, you get B is equal to, so let's see, is there a factor of 1/2 here? No, I think you will get a total of mu naught sigma V naught and then Y hat, right? So the magnetic field above the plate will be in this direction. Between the plate, it will be in this direction. And then below both the plates will again be in this direction. So this is the setup that we have. Okay. Is this clear? Now, and what is the electric field? The electric field again is equal to I'll write it as gamma V naught times E naught. What is E naught? E naught is the electric field in the rest frame of the plate. So the electric field in the rest frame of the plate, or I'll just write it as sigma by epsilon naught. Sigma is the charge density as seen by this observer. Okay, so I won't worry about the situation when they are at rest. I'll just look at the charge density of the moving plate, the apparent charge density. So I'll get sigma by, let's see, right? And if you want to write it in terms of the rest frame of the plate, you will just put a gamma V naught, sigma naught by epsilon naught. Sigma naught is the charge density in the rest frame. So now we introduce a third frame of reference. Well, it's actually not the second frame of reference. As usual, O prime, and O prime is moving with respect to O at some velocity V. Okay, again parallel to the x-axis. So now what happens to these plates? The velocity of the plates relative to O prime I'll call that V prime. Okay. And what is V prime? V prime is going to be equal to the relativistic sum, or in this case, the difference of these two velocities is going to be V minus, it's going to be V naught, or what am I saying? Right. So let me call it V naught prime. So the velocity of the plates relative to O prime is going to be V naught minus V over 1 minus V naught V by C square, right? Just by our usual relativistic velocity addition. So now we can use this V naught prime to calculate the quantities, the electric and magnetic field as seen by the observer O prime. But now we have to keep, account for the fact that the area of these plates will undergo Lorentz contraction with respect to O prime, right? So A prime will be equal to lambda V, A by lambda V, right? Area Lorentz contracts. And now again, I can write down what the electric fields are going to be. The electric field in the perpendicular direction will, just by exactly the same calculation that I did earlier, it will be the Lorentz dilated version of this E, right? So this will be equal to gamma V times E, right? Okay, but we already know that. What about the magnetic field? The magnetic field now is this expression, right? So we have the magnetic field B is equal to 2 mu naught sigma V naught, and then what was it? Y hat, right? This is the magnetic field as seen by the O observer. So what is the magnetic field as seen by the O prime observer? Well, it will be equal to 2 mu naught Again, by the same reasoning, you can again, the thing that will change is sigma prime is going to change and V naught prime is going to change, right? Both of these quantities are changing. So what do we get? We get that B prime is equal to 2 mu naught. How does sigma change? Sigma change by sigma is reduced, right? Because the area is reduced. So sigma becomes sigma by gamma V. And what is this velocity? This velocity is V naught minus V, 1 minus V naught V by C squared. Okay. So this is the magnetic field as seen by the moving observer. All right. Now, what about so now we have the electric fields and the magnetic field, right? One second. Sorry, my mistake. Yeah, the charge density increases by a factor of gamma V, not decreases, because the area contracts, so the charge density increases. And this is okay. This is okay. One second. Charge density increases. Okay. All right. So what needs to be done is the following. So we look at let's look at this charge density. This charge density is at the center of everything, right? So sigma naught is the charge density in the rest frame of the plates. That is when the plates themselves are not moving at all. That means V naught is equal to 0. Sigma is the charge density of plates with respect to O. And sigma prime is the charge density with respect to O prime. All right. So now, right. So what is sigma prime in terms of sigma naught? First of all, sigma prime is going to be equal to gamma v naught prime times sigma naught. Just look at this equation and convince yourself that this equation is correct. Sigma naught is in the rest frame of the plate. V naught prime is the velocity of the plates as seen by O prime. So sigma prime is this quantity, right? What is sigma? Sigma is equal to gamma V naught times sigma naught, right? So again, you have to be a little bit careful, and I was not careful, is that one cannot, so you see, I can relate sigma prime to sigma naught in this way, and I can relate sigma to sigma naught in this way, right? So sigma naught becomes sigma by gamma V naught. And so if I try to relate sigma prime and sigma, what do I get? I get gamma V naught prime over gamma V naught times sigma, which is not the same as, right? What was I doing? I was being hasty, and I wrote down that the area is Lorentz contracted, that the charge density sigma prime, right? Here I assume that sigma prime is just equal to gamma V times sigma, where V is the relative velocity of the two frames of reference, right? But this is not correct. This is not true. So this is also not correct. So you need to understand why that is the case. Okay. Right. And this is not equal to gamma V times sigma. So you can compare sigma prime to the rest frame charge density, and you can compare sigma to the rest frame charge density, but you can't compare them to each other in the same way. Okay. Important to realize this fact. This is at the core of the whole issue. So now we can write down, we have to look at this expression, sigma V naught prime by gamma V naught prime by gamma V naught. And what is this? This is root of 1 minus V naught square by C square, root of 1 minus V naught prime squared by C square. Gamma V naught prime and gamma V naught, this quantity and this quantity. Okay. And now, what is V naught prime? V naught prime is, I know what V naught prime is. I can write V naught prime here. Right. So now, as Griffith says, with a little algebra. Okay. So I will leave that to you. You can show that this expression, right? Because what do we want to do? We want to write down, we want to get rid of which term? We want to get rid of the V naught term. We want to write everything in terms of V naught prime. right? Sorry. So we want to write everything. We want to get rid of V naught prime, right? So you will have to substitute this expression in here, do this little algebra, and you will get 1 plus V times V naught by C square over root of 1 minus V square by C square. Okay. And this can further be written as gamma V times 1 plus V naught by C square. Now the thing is that if you look at this expression, it might remind you of the expression that I had in my previous lecture, when we were doing the same thing, and you remember this ugly looking expression. This expression was needed when you wanted to look at the transformation of the magnetic field. By the way, you guys have a class now? Sai, do you have a class now? Anybody else? Prasanna, Leon? Do you have a class right now? Manikant, do you have a class right now?
Sir, at 9:15.
9:15. Okay, I'll just take 5 more minutes then, right? So you see this expression, which is the ugly looking expression, for which I didn't give you a derivation. This was needed if you want to look at the transformation of the magnetic field. And now here we get another not so pretty looking expression. And these two are equivalent. They are basically saying the same thing. Okay. So this is a little bit more easy to see rather compared to this guy, right? So I'll just put it here for reference. Okay. So this one looks kind of complicated, and maybe you might not understand how to derive this. But this expression, you can see that it just involves algebra, substituting this relative velocity in here, and then with a little algebra. Okay. So this is homework number 2. Have I already given you some problems for the second homework set? How many have I given you? I don't remember. So exercise number, well, whatever is the next number. Okay, so once you have done all this, what you find is that the electric field in the moving frame, so this electric field in the moving frame where is it? Right. So the electric field in the moving frame is going to be equal to this gamma V naught prime by gamma V naught times E, and that is equal to this quantity. times E okay, and there is a sign error that I'm making somewhere. I think this has to be because of the negative signs over here, you will get a negative sign over here also. You get a 1 minus and a 1 minus and a 1 and a minus. Now, what is this quantity? This quantity is equal to if you look at the first term, it's equal to gamma V times the electric field, right? And well, we already know that this is going to be one component, but then you also get a second component. What is this component? This component arises, and so what is this second component? So if you write down the electric field, the original electric field, remember, is equal to sigma by epsilon naught, right? So I can write the second term as gamma V naught sigma by epsilon naught, and we get a C square, and this is equal to right. So I'll remove these vector signs for the time being, okay? And I will just write the electric field as having a Z component and the magnetic field as having a Y component. So I let Ez prime, Ez like this, Ez prime, Ez prime, sorry, no prime here, Ez. Now, in this expression on the right hand side, what do we have? We have the product of we have V naught and sigma. And what is V naught and sigma? Well, V naught and sigma is equal to the magnetic field, remember? So I can write this as gamma V Ez minus gamma V so I get C square and epsilon naught. 1 by C square I can write as mu naught epsilon naught. So what happens? 1 by C square times 1 by epsilon naught is equal to mu naught. I'll just get mu naught V, and then V naught times sigma. And mu naught V naught times sigma is equal to By, this quantity. Well, there's a factor of 2 again, but I'll not worry about that for the time being. And so finally we get this relation that Ez prime is equal to gamma V Ez minus gamma V times V times By. Okay. So what you can see is that the electric field is getting a contribution from the electric field, this Lorentz dilated electric field, but it's also getting a contribution from the magnetic field. And this contribution arises Exactly why? It arises because of the fact that when you look at the charge densities, they have to be related in this manner, right? So what are all the quantities in this expression? Ez and By, these are the electric and magnetic fields as seen by the observer O. V is the velocity of the observer O prime relative to O, right? And gamma V is the Lorentz factor. So what have we done? We have started with a reference frame O, in which there is some electric field, let's say in the Z direction, and some magnetic field in the Y direction. And then we look at the observer O prime, moving with respect to this at some velocity V. What do we find? We find that Ez prime has a contribution from Ez. So it's a function of both Ez and a function of By, right? So it depends on the velocity V and B. And these two terms, you see, can be seen as the components of V cross B, because V is in the, so the electric field is entirely in the Z direction, keep in mind, right? And V is in the X direction, B is in the Y direction. So this becomes something in the Z direction. And why is E entirely in the Z direction? Again, because of the reasoning that I gave you earlier, which is this fellow. There is no tilting of the electric field that happens. So the electric field in both of the frames of reference has to be perpendicular only. So this is the thought experiment, and I guess it's not that trivial, but it is definitely much more physical than just working with the force 4 vectors. So when we finish all of this, what we'll be left with? We'll be left with the, let me write down the final expression. Okay. So we will get Ex prime is equal to Ex, the parallel component doesn't change. Ey prime is equal to gamma V Ey minus V times, and I'll just change to Bz now, okay? And right. And then Ez prime, the same exact way we'll get that Ez prime is equal to gamma V Ez, but I'll get plus V times By. Similarly, for Bx, I'll get Bx prime is equal to Bx. And you can summarize these equations as follows. You get E is equal to, you get E perpendicular prime is equal to gamma V E perpendicular plus V cross B, and E parallel prime remains the same. And similarly, what you find is for the magnetic field, we get that B perpendicular prime is going to be equal to gamma VB perpendicular. And now you'll get a minus sign here. V cross B. V cross E by C square. And B parallel prime is equal to P parallel. Okay. So then another exercise for your homework is that derive the magnetic field transformations using Ampere's law applied to a loop of current as seen in two different inertial frames. Okay, so you have a loop of current, it creates a magnetic field. The magnetic field is equal to mu naught I by 2R. So you look at what happens to this when you consider the direction of motion to be parallel, right? And what happens when you consider it, take it to be perpendicular, right? And so in this case, you might need to consider the flux instead of the magnetic field strength, and you might need to take the loop to be, well, you might need to take the loop to be a square or a rectangle instead of a circle. Okay. All right, so I'll stop here. Thank you for your time. Sorry, Manikant, for running late. Please apologize to your next instructor for me. And I'll stop the recording and the live stream.